Welcome to Real Analysis Basics B5, Limit Superior and Limit Inferior. A sequence may refuse to converge, but each tail still has an upper and a lower bound. Apparently, disorder also leaves paperwork. We will turn those tail bounds into limit superior and limit inferior. Compute several examples and prove the convergence criterion. The n-tail, Tn, is the set of terms ak with k at least n. Increasing n deletes more early terms, so the tails form a decreasing family of sets. Limit superior and limit inferior ask how the supremum and infimum of these tails behave. The first 17 terms no longer get lifetime appointments. For a bounded sequence, define un as the supremum of the n-tail, and ln as its infimum. Every term in that tail lies between ln and un. These are the tightest lower and upper bounds, whether or not any term actually reaches them. Because Tn plus 1 is contained in Tn, its supremum cannot increase. Thus un is decreasing. For the same reason, removing terms cannot lower the infimum. Thus ln is increasing. The two tail walls can only move inward. Since un is decreasing and bounded below, it converges to its infimum. That limit is the limit superior of an. Since ln is increasing and bounded above, it converges to its supremum. That limit is the limit inferior of an. Every tail infimum is at most the corresponding tail supremum. Passing to the limits gives limit inferior at most limit superior. If the two remain separated, the sequence has at least two different long-term levels. If they meet at a finite number, convergence is waiting nearby. For unbounded sequences, we use the extended real numbers. Tail suprema or infima may be positive or negative infinity, and the same definitions still work. The empty set conventions are included for completeness. Though an ordinary sequence tail is never empty, analysis enjoys labeling even the unused emergency exits. First, let an equal 1 over n. Each tail supremum is 1 over n, while each tail infimum is 0. Even though 0 is not a term, both tail bounds converge to 0, so the limit inferior and limit superior are both 0. For negative 1 to the power n, every tail contains both negative 1 and 1. Therefore every upper tail bound is 1 and every lower tail bound is negative 1. The limit superior is 1 and the limit inferior is negative 1. The gap records the oscillation that ordinary convergence refuses to ignore. Now add 1 over n. The even subsequence approaches 1 and the odd subsequence approaches negative 1. The small perturbation disappears, so the limit superior is still 1 and the limit inferior is still negative 1. Long-term extremes are not impressed by temporary decoration. For an equal to n, every tail is unbounded above and its infimum tends to positive infinity. Thus both limit inferior and limit superior are positive infinity. If the odd terms are 0 and the even terms grow, the limit inferior is 0 while the limit superior is positive infinity. For negative 1 to the power n times n, every tail reaches arbitrarily far in both directions. The limit inferior is negative infinity and the limit superior is positive infinity. So equality at positive infinity describes divergence to positive infinity, not convergence to a real number. The word finite will matter in our criterion. For a bounded sequence, the limit superior is its greatest subsequential limit, and the limit inferior is its least subsequential limit. Bolzano-Weierstrass from B4 guarantees that subsequential limits exist. Now we identify the extreme ones. Let a subsequence ANJ converge to X. and call the limit superior u. Each ANJ is at most the upper bound of its own tail. UNJ. Because UNJ converges to u, order preservation gives x at most u. Thus u is an upper bound for every subsequential limit. To reach u, choose nj successively later so that unj is less than u plus 1 over j. The definition of supremum gives a tail term akj greater than unj minus 1 over j. Choose nj after the previous k-index. So the k-indices increase. Then akj lies within 1 over j of u and therefore converges to u. Hence u is itself a subsequential limit and dominates all the others. The limit inferior statement follows by the symmetric argument with infima. Here is the convergence criterion. The sequence an converges to a finite real number L if and only if its limit inferior and limit superior both equal L. Assume first that an converges to L. Given positive epsilon, choose n so that every ak with k at least n lies within epsilon over 2 of L. For n at least n, the entire n tail lies in that same interval. Therefore its infimum and supremum lie between L minus epsilon over 2 and L plus epsilon over 2. Thus both Ln and un converge to L. By definition, the limit inferior and limit superior both equal L. Conversely, suppose the limit inferior and limit superior both equal the same finite L. Then Ln and un both converge to L. For sufficiently large n, Ln exceeds L minus epsilon and un is below L plus epsilon. Since Ln is at most an and an is at most un, an lies within epsilon of L. Therefore an converges to L. The two tail walls squeeze the sequence. And for once the word squeeze is doing actual mathematical labor. The extended versions are also true. Equality at positive infinity means divergence to positive infinity, and equality at negative infinity means divergence there. The preliminary series represented a real number by its Dedekind cut. For each an, let Cn be the rational numbers strictly below an. It also defined set limit superior as points belonging to infinitely many sets, and set limit inferior as points belonging to all sufficiently late sets. Membership translates directly. A rational Q is in the set limit superior exactly when Q is below an infinitely often. It is in the set limit inferior exactly when Q is below an eventually. But the numerical and set constructions are not literally identical. Take an equal to 1 over n. Both numerical limits are 0. Both set limits contain every rational Q at most 0, including 0 itself. That set has a greatest element, so it is not the Dedekind cut for 0. One boundary point has filed an unauthorized extension. For finite numerical values, the exact statement needs cut regularization. Define R of E to contain Q when some larger rational P still belongs to E. This removes a possible greatest endpoint. After regularization, the set limit superior becomes precisely the cut belonging to the numerical limit superior. And the same statement holds for limit inferior. For example, if Q is strictly below the numerical limit superior, choose a rational P between them. Then P is below infinitely many an, placing Q in the regularized set limit superior. The converse and the limit inferior argument are analogous. To summarize, decreasing tail suprema define limit superior, and increasing tail infima define limit inferior. For bounded sequences, they are the greatest and least subsequential limits. A sequence converges to a finite L exactly when both values equal L. The Dedekind cut connection is exact only after removing a possible endpoint. That is all for B5. Every tail reports the remaining extremes.